Okay, so last time we started talking about parsing, and we will continue talking about parsing. Today I will give you two attendance. I will give you two parsing algorithms. Both of them will be based on dynamic programming again, and one of them will be top-down parsing. The other one will be bottom-up parsing. And after that, we would be done about this parsing based on the context-free grammars. And as I said before, context-free grammars are not the only way of defining a formal grammar for a language. There are other types of grammars, or there are other type of parsing systems, and we are going to look at them, namely dependency parsing. So today I am going to do this CKY parsing and bottom-up parsing, top-down parsing, early parsing. Okay, we looked at this one last time again. And parsing means, in this case, assigning a proper tree, a parse tree, to a given sentence or piece of text. And for this, we defined a grammar for a system, for a language. Okay, and these were the assumptions, and we said that these assumptions, some of them are really strong assumptions, but that's what we are going to do. Okay, we have all the words already in some buffer, and we won't worry about the morphological analysis, which is a big problem for Turkish, and we know all the words. Okay, so we did top down and we did bottom up. This was the top down strategy. Okay, from this grammar we can derive many different trees. So with the top down approach, if my sentence is booked at flight, okay, I am trying to reach to this tree here. Okay, so every branch of this search tree is another tree. So this is first tree, second tree, and third tree, and we expand each of them. Some of them will go to this book that flight explanation of the sentence. This was the top down, and we have the bottom up later. We start with the sentence itself, and we come up with all compatible subtrees. And when they grow, we hope to come up with a complete tree that explains the whole thing. Okay, so this is the bottom-up search. So let's do this using an algorithm. Okay, and while doing this algorithms, we should not forget about this ambiguity, because there is no single way of parsing a tree. Tree parsing could be ambiguous. You can explain the same sentence using more than one tree, and you don't know at the parsing stage, you don't know which one is true or not, correct or not. So who is going to determine? Sometimes we won't. Sometimes a later phase of parsing will later phase of NLP will make this decision, maybe based on the context or semantics of it. But that's not our problem for now. We just report the trees that we found. Okay. The second thing is the shared subproblems. Okay. That's important because when we are parsing trees, we keep solving the same problem over and over again for the same part of the sentence. Maybe we should keep all that information in a place and keep reusing them all the time. That will make our parsing algorithms more efficient. That's what we are trying to do actually with the dynamic programming. Okay, so ambiguity, we already know that. The sentence is this: I shot an elephant in my pajamas, and it's both sentences. Okay, translate this into Turkish and translate this into Turkish. The left one, on the left one. How do you translate this into Turkish?
Benim bir canım giyen bir fili öldürdüm.
Vurdum. Yes. Benim pijamamı giymiş bir fili vurdum. Or I have an elephant picture on my pajama and I am shooting it, maybe. And this one is, how do you translate this?
Giyerek bir fili öldürdüm.
Pijamamı giyerek bir fil. Well, I wouldn't say giyerek, pijamalıyken bir fil öldürdüm. Bir fil. It's not öldürdüm, it's vurdum. Okay? Okay. Okay, so it is interesting that the only non-native speakers of Turkish is answering this question in class. I don't know, the rest is sleeping. Some of you are literally sleeping. Okay. Good. So, what are we going to do? When we parse this sentence, I shed an elephant in my pajamas. Okay? We need to report both of these trees. Okay? Like we did with the morphology. Okay? Yeah, there might be more than one. We need to be both efficient and we need to report all this, these possible stuff. Shared subproblems is the key for being efficiency. So when we do this, okay, a flight from Indianapolis to Houston on TWA, okay. So from Indianapolis to Houston could be part of the same nominal. In this case, no, it is flight from Indianapolis. So but whatever you do, this one, this one, this one, or this one will be grouped together. They are forming a same constituency. Whatever you are doing, like in this case, okay. This propositional phrase doesn't matter how many different parses I can produce out of this sentence, will be grouped together. Okay, will be grouped together in my pajamas. So I don't have to solve this problem for different parses. That's what we mean by shared subproblem. So keep that information, subproblem solution information somewhere, and use it over and over again. That's what we do with the dynamic programming. Actually, remember what was the dynamic programming principle of optimality? You say that if you have an optimal path between 2 points, all the points that you go through in your optimal path has to be part of the optimal solution. So optimal solution to the subpart of the problem is dependent on the whole global solution. So that's what we are going to do. So those optimal solutions, sub-solutions, if I keep them somewhere, that's going to be useful for my global optimal solution. That's what we are saying. Okay. So without talking too much, actually, let me start talking about this algorithm, my algorithm. Okay, dynamic programming algorithm. They both will be, this one will be a bottom up approach, CKY, and this one really is top down approach. Both of them are kind of polynomial time. Well, I mean, depending on what you define as your basic unit of processing, but they are polynomial time, that's not exponential time. And they try to fill in a table, and a two-dimensional table and one-dimensional table, and they can produce ambiguous structures as structured as well. So that's nice. So let's look at the CKY parsing. Okay, so CKY parsing is a bottom-up parsing method. It is nice. It is very well defined. It is very logical. You can remember the rules and everything of the parsing method. But it says that to be able to work, I need binary rules. All the rules has to be that way. If you have a grammar, grammar has to be either A, B, C, all of them are non-terminals, or it should be A alpha. Okay, this is terminal. No other type of rules are accepted.
Beta alpha is not accepted.
This is a terminal, these are non-terminals.
Yes, so A beta alpha is not accepted in CKY, right?
What's it again? Say it again.
A beta alpha.
Yeah.
B alpha, sorry.
Like this? No, it is not accepted. No, it's not accepted. So this is bad. Okay, this is bad. So, well, nice thing is that given any grammar, any kind of context-free grammar, they can be represented using in this binary form. Sometimes we call it Chomsky normal form. There is a proof for that, and we are going to work in this form, in this binary form. And it will be clear in a few minutes why we are preferring this kind of a form. Because we say that starting from the top, when you say sentence, verb, phrase, noun phrase, verb phrase, okay? When you do that, this one says that you can actually divide a sentence into two parts. That's what it says, right? That's what it says. You can divide the sentence into two parts. One is the noun phrase part and the verb phrase part. And when you do the noun phrase part, for example, it is determiner and noun. You can divide the noun phrase into two parts too, and determiner and noun. But at the end, you have to have things like this: noun, for example, Ahmed, and determiner, for example, the. Okay, so these are the rules. These are the grammar rules that can be used with the CKY parser and nothing else. Okay, so let's go back to this idea of dividing a sentence or giving a constituency in two parts. Okay, so we will make a search. Maybe let's say I have elements from element number 1 to element number n in a given sentence. So there are n words. So in a way that I am making a search. Am I dividing this sentence from, okay, let's do 2, 3, dot, dot, dot, dot. Am I dividing the sentence like this, or like that, or like that? You got the idea. So this is a linear search, right? It's a linear search. So how am I gonna divide this S into two? So the thing is that we are going to test all of them, and some of them will be okay, some of them will not be okay. So at every level, at every application of the rules, we will be doing this search. And if I for example, if I did this noun phrase, verb phrase division like that, I am going to do the same search for this noun phrase and verb phrase part 2. Okay, again, both of them will be linear, and all the results that I get will be stored in a two-dimensional table, and at the end I will tell you what kind of sentences I can parse out of this set of words. That's what we are going to do. That's why we need these binary rules. Okay, theoretically it can work with ternary rules too, okay, because I am going to divide my grammar into the sentence into 3. That would be a little bit more expensive, and that wouldn't give us any more advantage over that. And so let's do this for the binary rules, and everything would be equivalent. So okay, consider the rule ABC. If there is an A somewhere in the input, then there must be a B followed by a C in the input. That's the main thing. Okay, so if A spans from I to J, then B has to be between I and K, then C has to be between K and J. So look for this K, or test all the possibilities of that K. Okay, that's the idea of it. So, but if your grammar isn't binary, then we are going to convert everything to binary. That's what we are going to do. And the theory says that any arbitrary context-free grammar can be written into a binary form, Chomsky normal form. And what does that mean? It means that if I have a grammar, input grammar, if I convert it to the Chomsky normal form, whatever the original grammar accepts, I will accept. Whatever it rejects, I will reject. but my parse trees will not be the same. My parse trees will be a little bit different because I am changing my grammar. I am changing my grammar, but coming back is not that difficult. Okay, so all the rules has to be this way. Okay, all the rules has to be this way. Let's look at this one, for example. A, B, C, and D. Okay, so this is not a binary rule. How can I make this a binary rule? This is what you do. You say A, X1, D, and X1 is B, C. So that's it. So I made up a new rule, X1 rule, new terminal. Now both of them are binary now, right?
How about AAB? Does that work?
A, you mean like this?
No. A, big A, B. So non-terminal A. Yes.
Well, this is already in binary form.
Not accepted.
What do you mean?
So the recursive.
Well, without the recursive rules, there is no context-free grammars, right?
Okay.
True, but this is already accepted. But if you are doing this is a bad thing.
Yeah,
This is
this
bad.
not accepted.
Okay, how can I handle this one, A, B, because I don't accept these kind of stuff.
You make
How?
alpha x2 and make it ax2b.
Exactly. So you would do A x2b and x2a and etc. Okay, good. How about this one? If I have A, C.
Not accepted.
How are you going to handle this one? Well, I mean, at the end, C has to be going somewhere like A, C, B, C, D, right? So you write all of them like A, B, and A, D. But that fixes it all. So I remove C. Okay, so there's always a solution, and this is an automatic. This can be automatically done. It is very easy to convert, so I can get the binary form without any problems. Good. Okay, so we talked about this. Again, we are trying to do this binarization so that I can cover the whole sentence in two parts, and I am trying to find the middle position where it is. Well, I am not trying to find a single middle position. I am trying to test all the middle positions, okay, to see if they are producing any meaningful parsers out of this tree. Okay, so that's the binarization why we are doing it. Let's look at the binarization of this grammar. Let's try to do it together. Okay, this one is fine. This one is fine. This one bad. This one is bad. So what are we gonna do now? We are going to say S x1 VP, and then x1 is auxiliary NP. I handled it. How about this one? SVP. Well, VP goes to verb, and verb goes to book include prefer. What else did I said? So S goes to book include prefer. Okay.
Can you just say S goes to verb? Oh, verb is not the term. Not
Yeah, verb is not a terminal either. So it has to be S book, S include, and S prefer. Okay. So sometimes it is. I mean, definitely this one is easy to read for us for humans. but this one is good for this for this CKY parser. Again, CKY parser works on this grammar. Whatever it parses, it produces a parse tree that's compatible with this grammar. So the original grammar will be a little bit different than what we are producing. But again, so most of the time it is more important to know if the sentence is parsable or if there are any ambiguities in it. Okay, so it is already done like that. Okay, so let me get rid of these. Without the glasses I can't see now. This is our L1 grammar. This is L1 grammar is Chomsky normal form. As you see, this SVP became would include prefer and verb NP. I think the NP, yeah, this one. Yeah. So I placed this with verb NP. And then what? Yeah, I replaced this verb NP with X2, I guess. So of course this is not the complete grammar. I got rid of some of it. I'm not showing it, but this is the part that we are going to use for our CKY parser. I forgot the names of those guys. CKY. Those are the initials of the authors of this algorithm. Okay, good. So I am going to do this. Let me erase this part so that we can do it. Okay, we are going to build a table so that a spanning from I to j input is placed in cell ij in table. So table is a two-dimensional table, and in each box of the table, by the way, it's a two-dimensional, but it's a triangular. So it's kind of, we don't use the lower part or the upper part depending on how we are doing it. Okay, so this table in it, there are cells. Cell ij means that what kind of constituency can I put in between I and j? So hopefully in the cell of 0n, there is an s, because 0n means that starting from the beginning of the sentence to the ending of the sentence, okay, I can produce an s. That's what it means. Okay, so we are doing this from bottom up. What does that mean? First, we are going to start talking about cell number 01, then 1, 2, 2, 3, etc. So we are looking at each word one by one, and then we are going one level up. How about 0 to 2, 1 to 3, etc. It's going that way, and that's how the algorithm is going to be. And at the end, when I hit this cell 0n, I will find all the possible parsings of this whole sentence. Okay, and every time when I do this 0 to n, I will iterate over to between 0k to 01 to 1n, 02 to 2n, 03 to 3n, but each time each of them will be available in my parse tree, parse table. Okay, so maybe do it already. So what did we say? Let's do this. My sentence is book the flight. Okay, if I'm going to do that, book the flight, and this is my table. Okay, this is 0 to 1. I can do it this way: 0, 1, 2, 3. Okay, This is 0 to 1. This is, okay, 1 to 2 and 2 to 3. You can go that way, okay? So 0 to 1 is here, okay? Book. What kind of explanation can I have for the book? I just go there, this one. So there is an S here.
No.
There is an S there, okay? And what else? Book and verb phrase, and there is a verb phrase, right? There is a verb phrase, VB, what else?
Nominal.
Nominal, yeah, there is a nominal. So these are the things that can happen for the book. Okay, so that's all I think. So how about this 1 to 2? Okay, how about this 1 to 2? For 1 to 2 there is the. For the which one do I have? I think I have determiner. Other than that, do you guys? I think we don't see all the rules in here, right? So let me put this determiner here. And as that I don't have anything. How about this flight? So you know what I'm getting at, right? I am doing this 0 to 1, okay, 1 to 2, 3 to 2, 3 to 2 to 3, one word stuff. Or I can do this. How about let's go to this box. This box says that can you make sense of all the words from 0 to 2? To make sense of 0 to 2, I need to test it from 0 to 2, 0 to 0 to, okay, 0 to 0 to 0 to 2, or 0 to 1 to 1 to 2. So can I make any sense of nominal determiner, or verb phrase determiner, or sentence determiner? If even if them makes a sense, then I will put it in this box. But in this case, it doesn't make any sense. It doesn't make much sense. But I can do the same thing for this one, and we are going to see it. Let's run this in a real example, and we are going to see how that works. This is the complete algorithm itself. Let's ignore this algorithm for now, because it will be difficult to follow it without seeing the example. Let's see the example, okay? Okay, so this is the book the flight through Houston. Okay, that's the sentence. Let's write the sentence actually.
Can you zoom in, please?
What? What?
Zoom in demiştim. Hep gözükmüyordu hocam. O yüzden.
Do you see it now? Okay. Let's write this book. Book the flight through Houston. Okay, so the flight through Houston, or you know what I mean, right? The flight is noun phrase, propositional phrase, and this is again noun phrase 2, and this is verb phrase, and okay, like that. This is one meaning. Okay, another meaning would be book to fly through Houston. Through Houston would be a part of this verb phrase 2. Okay, this is verb, not right, verb phrase. So at the end I am going to have two different parsers. This is just one of the parse. Okay, so this is what it did. Okay, this is the rule actually. This is what we do. You go this way, and for each column you go up. Okay, for the 0, 1, 2, 3, 4, 5. Okay, 5 words. From 0 to 1 there is only one book. From the book I can make a sentence, verb phrase, verb, nominal, and noun. Okay, the fact that you have seen a sentence here doesn't mean that you parse the whole sentence. No, because book is by itself is a sentence, just one word sentence. If I say that I parsed everything, no, you ignore the rest of it. Okay, your parsing is not valid. Okay, I am done with this column now. This first column I am done. Now I am at here, so this one I am okay. I am going to do this way. Determiner and that's it. I cannot put anything. How about this one? This one says that is there any rule that has an as and determiner on its right side? No, I don't have it. Is there any rule that has verb phrase and determiner on its right side? No, I don't have it. Verb and determiner, I don't have it. So this box will be empty. That's why we have binary rules, you understand it? Okay? That's why we have binary rules. Okay. So let's look at this third stuff. Flight could be a nominal or noun. Okay, that's it. How about this part, 1, 3? So 1, 3, we are going to look at this. Between 1 and 3, between 1 and 3, okay, the flight. We are talking about the flight. Okay, between and 1, 3. So it could be from 1 to 2 to 2 to 3. So determiner nominal, determiner noun, yes, it's a noun phrase. Okay, so determiner noun is a noun phrase. So there is a rule says NP determiner noun. So I put noun phrase here. So that means what? I can produce a noun phrase between elements of 1 and 3 and put it in here. So what did we say? We are doing this bottom up really. I mean, we are trying to make sense out of the words and the, anything that can be produced out of those words. Whatever we find, we'll place them in these boxes. So the idea of not solving the same problem over and over again is happening, because if anybody needs to look at this between 1 and 3, this is the only thing. These are all the things that can happen between 1 and 3. Okay, let's get to 0 to 3. So for the 0 to 3, it could be either 0, 1 and 0, 1 and 1, 3, right? Or 0, 2, 0, 2 and 2, 3, right? Either this combination or this combination. Okay, can I have anything out of this combination? Yeah, I guess verb phrase, noun phrase makes a sentence, right? So I put sentence in here. Okay, what else? Verb phrase, noun phrase makes a verb phrase too, and I put in there. Okay, what is X2? I forgot about X2. X2 is verb noun phrase. Okay, I guess it is available there too. Okay, so X2 is verb and noun phrase. So verb is here, and of course noun phrase is here. Okay, so all of these three are happening because I have some nice combinations between these two boxes. 1 to 3, 0 to 1, and 0 to 1, and 1 to 3. Okay. How about this one? This one and this one doesn't happen because this box is empty. Doesn't happen. Good. So this one says that I can make a sentence out of these 3 words. Book the flight. I can make a verb phrase, and I can make an X2. Okay, I'm done with this column now. Let's look at this column. Okay, so between 3 and 4, through is a preposition. Okay, I make a prep. How about this one? 2 and 3. Can I make, okay, 2 and 4. Can I make nominal prep, noun prep, a rule that has nominal prep or the noun prep on the right side? No, this will be empty. How about this one? 1, 2, and 2, 4. This is empty, right? 1, 3, and 3, 4. Noun phrase prep. Is there such a rule on the right side? No. So unfortunately, I couldn't do anything. This will be empty. When I come to this one, 0, 1, and 1, 4, this one is empty. Empty and empty. Well, none of them will be, okay, there will be no rule that ends with a prep on the right side as the second element, non-terminal. So this will be empty too. When I come to this one, okay, this 4, 5 is Houston. It is either noun phrase or proper noun, okay? And 3, 5 is, what is 3, 5? From 3 to 5. Preposition, noun phrase, yes, that makes a prepositional phrase. Or preposition, noun phrase that makes another prepositional phrase. So I can put this PP here. How about 2, 5? 2, 5. 2, 5. 2 to 3, 3 to 5. Noun, nominal and prepositional phrase. Yes, that's a nominal and a nominal. Okay, how about this one? This one will not work because this is empty. Okay. And doing the same thing here again, and I will come to this one. This one says that, where does this S come from? Tell me where this S is coming from. What is this S? It is S is 0 to 1 and 1 to 5. Is this logical? 0 to 1, 1 to 5? 0 to 1, verb phrase, 1 to 5 is noun phrase. Yeah, verb phrase, noun phrase is an S, right? S is a verb phrase, noun phrase. Yeah, we did that. Okay. And also, verb phrase, noun phrase is another verb phrase. And also it's an X2 too. Okay, what can I do now? Can I do something with this one? 0 to 2 and 2 to 5? No, I cannot because this is empty. How about this place? 0 to 3 is a verb phrase. 3 to 5 is a prepositional phrase. Verb phrase, prepositional phrase. It makes a sentence, right?
No.
Verb phrase, prepositional phrase.
Makes,
I think it's a sentence.
no.
Let's look at it. Yeah. Yeah, I think there is a rule for that. Verb phrase, prepositional phrase.
Verb phrase, no.
Verb phrase, yes, here it is. Verb phrase, prepositional phrase. Book through Houston, right?
Okay.
Book through Houston. Through Houston is prepositional phrase, book, yeah. Go through Houston, yes. So verb phrase, prepositional phrase makes another sentence. So I am going to put another sentence in here. But this sentence is because this one and this one. The other one, let's look at the other one. Let me mark it with the different color. This one is because verb phrase 0 to 1 and then 1 to 5 is noun phrases here. This one. Okay. So I have two S's in this box. That means there is an ambiguity, but I have recovered it. Okay. I have recovered it. Since this box is empty, I am not going to look at 0 to 4, 4 to 5. Okay? So what is the complexity of it? I am going over the columns. That means the number of words. Okay? And I am going this way too. Again, the number of words too. Okay? But for each of them, I am checking all of my rules if any one of them is matching it. So number of words times number of words times times the number of rules. So we are talking about n squared times something.
But other than that, there is also the number of possibilities for every word.
Yeah, for this one, I am checking this one. I mean, this k. K is 1, K is 2, K is 3, 4, and 5. This is in between. Remember, between I and J there is a K.
I mean 0, 1 has by itself multiple.
Yeah, that's what K is. So
Okay.
so this 0 to 5 means that 0, 5 means that K, right? Well, actually, it is what I am doing with this. No, well, I mean, I need to fill in all of these boxes. That is number of words. Okay. And for each one, I am going to scan this K and comes from there. And for each box, I am going to look at the number of rules, and this will be the complexity of it. And square R. Not bad, okay? It's in polynomial time, it's not exponential. It's in polynomial time. And the nice thing is that it gives me all possible parse trees for this grammar.
This is bottom up, right?
What? Yeah, this is bottom up, yeah, of course. Why? Because we started making sense of these words, okay? Okay, so we are when we are done, when we look at this table, do I have this complete table somewhere? Yeah, I think this complete table is here. When we look at this chart, okay, not only that I have these, by the way, I have three, I think I asked this question last time. I have three S's, the other one comes from the X2, okay, but S2 and S3 are the same thing in terms of our original grammar. Remember, we binarize our grammar. S2 and S3 are the same thing. When you look at this, not only that we have parsed the whole sentence, we have the sub-constituency assignments of them too. All of them are there too. And we started doing this from the bottom-up case. Okay? So you can come back and you can ask the question, the flight true, is there anything meaningful that I can assign to flight true? No, 0 for is empty. But the flight is, yeah, it can be many things including a sentence, verb phrase, and X2. Okay?
Flight can be only MP, right?
Flight by itself can be a nominal or noun, but the flight can be a sentence. How come a flight no, I'm looking at the flight is, okay, this is sorry 0 1, let me use a different color. 0 1 2 3 4 5. The flight is 1 3 1 3 is here. The flight could be a noun phrase. Okay. 0 2 is this, book the. There is nothing I can say about book the. Okay. No constituency. Okay. Good. So this is CKY parsing, and let's look at the algorithm. Let's go back and let's look at the algorithm. It makes more sense now. Looking at the algorithm, let me get rid of all of this stuff. Okay. So 3 loops, 1 2 3. Okay, the first loop, remember this is our table. First loop goes this way, this is first loop, and the second loop does this is our second loop, and the third loop scans for the K for each of them. Okay, so from 0 to length words, okay, this what is this? Tell me what this line is. Oh, I use too much time.
This is finding all the possibilities of a word inside the grammar.
Yeah. This is the one that looks at the, only this line looks at the rules of this type. Right? All the others are looking at these kind of rules, binary rules. This one, and also this one, places only at this diagonal here. Right? This one places the non-terminals in those diagonals. The rest of them is j minus 2 to down to 0. So this one is going up, and inside it I have this k. Can I make a sense out of this from I to k, then k to j, right? I to k, k to j. Do I see a b in I to k, and do I see a c in k to j? And there is a rule in my grammar set that goes from a to bc. Okay? Again, 1960s, very smart algorithm, very nice algorithm. As you know, in 1960s everything was invented, and we didn't invent anything after that. They were much smarter than, at least I am. I don't know you guys, but
At that time, the computational costs were very high, so people had to be more
smart.
inventive. These
So
days, it's just like
we get
add
to
more layers.
so
to
we
your
get to be
network,
we
and
get to
that's-
be stupid.
I mean,
We have, well, I
we
mean,
got lazy.
yeah, I don't know. Things have changed. Okay, so let's take 10 minutes of break, 15 minutes of break. 14:35, and I will look at the other algorithm, the top-down algorithm, earlier parsing. Can we open one of the all of the windows maybe? Where is my attendance? Here is it. Did everybody sign it? Tüh ya, kalem getirdim, o da çalışmıyor ya. Sırf imza atmak için kalem getirdim.
Tükenmez mi gerekiyor ya şey imzalarda.
Vereyim mi
Ama
kalem?
yapmadı. Ya bozulmuş ya.
Kalem vereyim mi?
Önemli bir şey var. Şimdi konuşmak var. Yarım saat kalmış. İyi para kazanıyor. Ne oldu? Görüşelim. Grupları iyi. Nerede? Kiye'ye mi gidiyor? Nereye gidiyor? Ha. Ha, bir daha. Deneyeceğim işte şu. Yok daha ödemiyoruz yani. Yarın yardım.
Yani akşam. Suyun mu?
Suyun değil de ödem var yani.
Yarın akşam.
Onu yapmam.
Emekli mi?
Onu da işte.
Başlayalım mı?
15. Başladım ya. Biraz da
Görüşürüz.
sevgi.
şey var. Ronaldo Messi.
Başka?
Messi kanka.
Başka yok mu?
Eskiden Ronaldinho vardı. Beşiktaş'ta şey vardı. Olcu Işan.
Okay, so this is the CKY algorithm. We looked at one example of it, and it is bottom up, so it finds all possible constituencies, even the ones that are not used at all. So that's kind of inefficiency. Maybe we can do just the other way of it. Only use the constituencies that are possible with these sequences. Then it is the early parsing. Okay. So for the early parsing, we don't have to change our grammar. Any kind of grammar is okay. You don't have to do the binarization, Chomsky normal form of anything like that. You start with the usual input grammar, and in this case, of course, you don't go up from the word to the sentence, final start symbol. You start from the start symbol, okay, and continue working your way down to the words themselves. Again, it is based on the table, and we are going to have this time a one-dimensional table, but inside the table, at each cell, there are many elements, sometimes hundreds of elements in it. So it is not two-dimensional, but don't think that one dimension is more simple than the two-dimensional CKY. It is as complex as the CKY in terms of memory requirement and runtime requirements. Okay. So the length of the table is n plus 1, n is the number of words, and inside this table we have this, okay, completed constituents, okay, a constituency that I have seen for all the words from the beginning of the sentence up to this point. There are some constituents in progress, okay. I am still observing those, and some of the constituents I am predicting. For example, at the beginning of the parsing, I am predicting an S, and this is shown this way. I am predicting an S. At the end of the parsing, if I have a symbol like this, I have observed a constituent S at the end of the table, then my parsing is complete. I found it. Okay, but if I have something like this, as noun phrase dot verb phrase, I have completed seeing this noun phrase. I am predicting a verb phrase. You would read it that way. So these are called dotted notations, dotted rules, and we are going to use them in our table formation. So let's look at them. Okay. So I am predicting a VP. Nothing happened yet, but I am predicting the VP. All the words that I have considered so far, I observe the determiner, and I am predicting a nominal, and this NP is in progress. And this one I have observed the VP. While observing it, I use this rule. Okay, a VP has been found. Okay, so predicted, in progress, and has been found. Okay, remember the table. The table is n plus 1 length. N is the number of words. Okay, this is what happens at the beginning. At 0, 0, I didn't read anything yet. At 0, 0, I am predicting a verb phrase. Also, I am predicting a verb phrase, noun phrase. I am predicting this and this and that and that, okay? At the beginning, we do that. Let's look at this one, book that flight, okay? So 0, 0, I have this one. Maybe between 1 and 2, okay, between 1 and 2, I have seen a determiner. Now I am predicting a nominal. And between 0 and 3, okay, verb phrase, verb and noun, I observe the verb phrase, okay? So these are the three things. Again, this is dynamic programming. We have a table of length 0 to n plus 1, and we are going to fill in that table. Let's look at the algorithm itself actually. Okay, see through the table from 0 to n. New predicted states are created by starting top down from as, and new incomplete states are created. I am predicting this. When I completed something, I say that I completed them. Okay, so this is kind of the algorithm, more formula written. Okay, at the beginning, predict all the states you can up front. Read a word, extend the states based on the matches, generate new predictions, go to step 2. Okay, when you are done with all the words, then you look at the chart to see you have a winner. You have an as start symbol at the last box of the table. Okay, so let's look at this one. What does that mean? Let's look at very simple grammar. As, noun phrase, verb phrase, and then our noun phrase is simply a noun, and or maybe just a noun phrase is simply a flight. Okay, and verb phrase is simply what am I gonna do with the verb phrase? Okay, let me. Now my phrase is just an I, and verb phrase is just read. Very stupid grammar. Okay, all I can do is just I read, right? So at the beginning, all the states are I am predicting this. I am predicting this will happen. Okay, noun phrase and verb phrase. But with the noun phrase, since I am predicting noun phrase, I have to predict this one too. Dot I, and that's it. These are all the predictions at the beginning. Okay, so these are the things that I am predicting. Anything that I see happening with the first word that I'm reading is that happened, then it looks like I am going to, if my sentence I read, it looks like I am going to extend this one because I am matching something and it will be completed. That's the idea of doing it. So put all the possibilities at the beginning in the first box of the box number 0 of the table. Then read the words one by one, do these extensions, generate new predictions, and etc. Okay, so let's look at the algorithm itself. So let's look at the for loops. One for loop here, another for loop here. But this one has other functions: incomplete, predictor, okay, scanner, and completer. These have loops in them too. Predictor for each, scanner, and completer for each again. A third loop comes from there too. Again, the complexity is around something to the cube. Okay, 3 loops, nested loops. Like I'm going to do it the way I did with the CKY parser. Let's skip the algorithm right now. Let's go directly to the example. Okay, book that flight. So I have box number 0, 1, 2, 3, and plus 1. I have 3 of them, 4 boxes. Okay, so at the beginning Okay, chart number 0. Put all of them inside 0. Okay. So it looks like, okay, this is a dummy rule, dummy start state. I am predicting an S. Since I am predicting an S, I am predicting a noun phrase, I am predicting an auxiliary, and I am predicting a VP. With the noun phrase, I am predicting a pronoun, proper noun, determiner. Okay, with the VP, I am predicting a verb, like that, okay? So these are the things that I am predicting. And still, I did not read anything yet, right? I did not read a single word, okay? So that means what? Given the grammar, chart number 0 is fixed. It is always the same thing. So given a grammar, these entries are the same for all inputs. They can be preloaded. But it's going to be a very large number of elements inside that chart number 0. Okay? So these are all predicting. Since I did not read anything yet, I am just predicting these will happen. So remember what was the definition of the top-down? Top-down expects something. I am expecting an S to occur. But if you are expecting an S to occur, either this one or this one or this one. So I am expecting 3 of them. If noun phrase is expected, then I have to expect all of them, okay? If word phrase is expected, I am expecting all of them. If auxiliary is expected, I am expecting all kinds of auxiliaries. So this is more efficient than our CKY. CKY, the problem with the CKY was it was figuring out all possible constituents. Now this one is trying to test all kind of top-down trees that are drivable from our grammar. Okay, so I put all of them in 0, 0, 0. So what am I going to do now? I will just read one word, okay, and I will see which ones are extending and which ones are going further. Okay, chart number 1. I read book. When I read book, okay, I scanned it, and now I observed this verb. I observed this book word. Now that means what? This rule is now complete. Okay, VP verb is complete. This one is moved from dot verb MP to verb dot MP. This one is moved, and this one is moved. See, in chart number 1, I have a sentence. Sentence is book. Okay, 0, 1. Since I have new predictions now, noun phrase, propositional phrase, I place them in my chart number 1. Okay, from 1 to 1, I am predicting a pronoun, proper noun, determiner, and preposition. Okay.
What do you find in, what do we put in 1, 1?
It's like at the beginning, remember at the beginning when we said these are all 0, 0, I did not read anything yet.
Okay.
This is 0, 0, so I am predicting these. So here I am predicting a pronoun at 1, 1 because I am predicting a noun phrase here. I observed a verb between 0 and 1. At 1, 1 I am predicting a noun phrase.
Okay.
I don't know, I mean, the important thing here is the beginning of the index, because I don't know the endings of it. Remember, I was predicting all of this stuff at 0, 0.
So when we read something, we put it below. When we predict something, it is to the right.
What?
So we are at 0, 0. When we read something, or when we observe it, we put it down here.
Yeah.
And the prediction will be next to it. And this
Are you
is
talking about the indexes?
Yes.
Yeah, you could say that, yes. If I observe something, I am changing the second index
Okay.
with the completers. With the predictors, newly introduced rules, I am predicting them now. I don't have any evidence for them yet, but I am just predicting them. Okay, and we continue and we read another word. Okay, when we read the other word, book, that, and I read that. So I scan this one, I completed this determiner, okay, and now I'm going to predict this nominal, right? And that's it. I am going to predict this nominal and this nominal and this nominal. These are all predicted. And when I read the last one, flight, okay, I completed this noun, I completed this noun phrase, I completed this nominal and nominal, and these are the predictors. PP, I'm going to predict PP. What else? I am going to predict a noun, but they didn't put it in here, okay? And I completed this one, verb noun phrase, and I completed this one as verb phrase. Since the third box is the last box, I am happy that I hit this S, because now I have a complete sentence that covers between 0 to 3. Okay? Good. So, I mean, it turns out that this is not any more efficient than the CKY parser, because it is trying to find all kinds of possible sentences or the trees that seem to be compatible with the current input, but most of them will not compete, will stay in half, right? Okay, so this is called early parser. If I go back to the algorithm again, I get the words and grammar, and at the beginning do this. NQ gamma goes to that S. This is the dummy rule. Okay, I'm going to run this loop from 0 to length of the words, and then inside each of those chart stuff boxes, for each state in the chart, I am going to ask this question: are you incomplete? If you are incomplete, if our next category state is not a part of speech, then I am predicting it. If it is in part of speech, then I found it. Then if it is not incomplete, I am going to do the scatter, and otherwise it will be completer. Scatter and completer and predictor are done that way. Predictor is, let's look at this one. If I have a rule like that, I am expecting a B, non-terminal B, for each of the rows that has B on the left. If they are in my grammar, okay, then I am predicting it. This one doesn't have anything to do with the word that I am reading, because they are predicting it. Scanner says that, again, the same thing, okay. B is part of speech word J, so it says that for the word number J, okay, if I can mark that word with that part of speech B, then I put this in my chart because I observed it, right? Yeah. And computer says this. Computer says this. If I have such a situation in chart, and I have, yeah, if I have this completed, if I have this, and for each case like this, for each predictor that is expecting a B, just replace it with this rule now, this chart state now, because I observed B. And I put this in chart number K, from G to K. Good. Okay, so as you see, there is for loop in each of them, and 2 for loops outside. So it is something to the cube. It is not any more expensive or less expensive than the CKY, but it is not in exponential time, it is in polynomial time. Any questions so far? Do I have anything else
Is
about
there any
this?
visualization for this for this algorithm, like the CY thing?
Well, visualization is this. I mean, this is the whole visualization. 0, 1, 2, 3. Chart series S. These are all the states. Okay. The other one was easier because
The other one was more visual.
yeah, because
Much easier to
in
understand.
each of the boxes you will have a limited number of constituents, but this one, especially for the chart number 0, you have thousands of rules, states. Okay. So again, going back to ambiguity, did we solve the ambiguity with the parsers? The answer is definitely no. We are not trying to solve any ambiguities. We are not trying to solve any ambiguities. We have only 6 people. Okay. We are not trying to solve any ambiguities. Ambiguities will stay there. The important thing is that we should not miss any ambiguity. Okay. All the ambiguities should stay there. Whoever is going to use these parsers, they should either address this ambiguity issue or they should keep the ambiguities as they are. Okay. No, both of them. Okay. They have multiple structures in the last table entry, either in the corner or in the last one. Okay. Good. I mean, for some reason, maybe it doesn't occur to us. I mean, almost all the sentences that we have are ambiguous, most of them. For some reason, we don't realize those ambiguities. We just get the sentence the way it is intended. That's the beauty of the natural language itself, actually. Although it is ambiguous, for some reason we can find our way out of these ambiguities without trying to come back and parsing it again. And it looks like we are doing it in real-time and incremental fashion. Not that both of these algorithms, they need the whole sentence to parse it, right? We don't work that way for some reason. The way we parse our sentences are a little bit different. Okay. Good. Any questions about? Remember what we did? We looked at the context-free grammars. We compared it with the regular grammars and context-sensitive grammars and the free grammars. And we looked at 2 ways of parsing context-free grammar-based natural languages in polynomial form. Okay, good. If there are no questions, I am going to start a new topic, which is the dependency parsing. Where is my? No, not this one. Not that one. Yeah, here it is. But maybe I should just simply. I mean, I don't want to skip this one. Just talk a little bit about it. Statistical parsing. Okay. Well, this is almost the same as the CKY, but the only thing is that we assign probabilities to each parse tree. Okay, each parse tree. So where do we get those probabilities? We get those probabilities from our data set, from our parse tree set. Okay, let me show you a few examples like that. Okay, so we say that if you are using a start symbol, sentence symbol rules, 3 of them, our statistics say that 80% of the time we have used this one. 10% of the time we have used this, and other 10% this. So total is 1.0, 100%. Okay? So for each rule we have a probability. And this probability comes from the data set. Okay? Whenever we use a determiner, 60% of the time it is the 20A and etc. So if I know this, I can assign probabilities for each parse tree. So this is a very good way of kind of solving the ambiguity, addressing the ambiguity. You will say that this parse tree is ambiguous, but this is the most probable one. This is the most probable one. So what are you going to do is, okay, if I have this, you just multiply all these numbers and you get this probability of parsing this tree that way. Book the flight to Houston, okay, or book the flight to Houston the other way, and this is this much. Okay, the difference is how many zeros? 4 zeros and 4 zeros. I think this one has twice the possibility, right? Okay, so I can maybe do the disambiguation this way. Probability context free grammars. And when you do this, you just multiply all these probabilities to get the probability of the constituents in the boxes with the CKY parsing. Okay, so that was the idea. I am going to skip rest of it, and at the end of this chapter or this slide set talking about tree banks, I'm going to skip those. Let me human parsing, I was going to talk about it. Okay, well, these are no problem for our CKY parsing or early parsing, but these kind of sentences are problematic for the humans. John put the dog in the pan with a lock. Okay, John put the dog in the pan with a bone in the car. You kind of parse them, but when you read the whole sentence, you need to sometimes go back and think about what we are doing. Okay, in the pan, what is in the pan? Where is the lock? Does the lock belong to the dog or the pan? And you need to think about them. You need to figure out the propositions and who is modifying what kind of stuff. These are usually called garden path sentences, and usually they give us trouble, and we when we read them first, we don't understand what's going on. For example, this one. Can you translate this into Turkish? The horse race past the barn fell. It looks like the horse raced. Raced is kind of the main verb of the sentence, but it is not. It must be fell. So raced past the barn is the prepositional phrase. Okay. How about this one? The complex houses marry students. It looks like the complex houses is the noun phrase, and then marry students that doesn't make much sense. The complex is the noun of the sentence, right? Houses marries is the verb part of it. Okay. The old man. It looks like you start the sentence like the old man. The sea. But where is the verb? The old is the noun. Man is the verb. How about the last one? While Anna dressed, the baby spit up on the. So it looks like while Anna dressed the baby. Okay, so it is not while Anna dressed the baby. It is while Anna dressed, the baby spit up on the bed. So incremental computation parsers can behave like humans, and they can encounter these kind of problems, and they will let you know that although the sentence is grammatically okay, people will have trouble reading these garden path sentences. People are confused about them. Okay. Good. This is grammatically possible. Okay. The rat, the cat chased, died. It's grammatically possible, and they use it a lot. But this is possible too. This is possible too. But this one is not used in practice a lot. The rat, the cat, the dog, the boy owned, bit, chased, died. You know this, right? The rat, the cat chased. Okay, the cat chased is the modifying constituent for the rat. Okay. In this case, the cat, the rat, the cat, the dog, bit. Okay. This modifies the rat, and this modifies the cat. You understand what we mean, okay? So we don't like these kind of stuff, these kind of recursive stuff, but we like this one, okay? Tail embedding, tail recursive stuff. The boy owned a dog that bit a cat, that chased a rat, that died. Okay, so both of them are grammatically possible, but we don't use them much. Okay, so let's move back to our original talk of parsing. We talked about context-free grammars. Now we are going to talk about dependency grammars, and I'm going to give you one way of doing this parsing of dependency grammars. As we said before, context-free grammars are not the only way of parsing a sentence. Dependency is a more looser way of parsing a sentence. All you do is you just find the binary relationships between the words in a sentence. John liked the dog in the pen. Okay, so there is a nominal subject relationship between like and John, and dog and like is a direct object. This is determiner. This is determiner too. Okay, so this is a type dependency parse. It's a tree, like a parse tree, but it only shows you dependency stuff. Does it have to be a binary tree? No, it doesn't have to be. Relationships are binary, okay, but the tree doesn't have to be a binary tree, okay. So these are called the dependency grammars, okay. And for some languages like Turkish, this is more reasonable. This is more reasonable because, I mean, these kind of languages are called free word order languages. As I mentioned before, ben okula geldim, ben okula ben geldim. Whatever you do with the word ordering, they are all meaningful, right? They have some kind of a meaning. So they all should be parsable. So what is the point of parsing them? Okay, I am all parsing them. They are all parsable. Okay, and always geldim is the verb of the sentence. Ben is the noun phrase of the sentence. Okay, okula is the prepositional phrase part of it. Doesn't matter, right? So our constituencies are not changing. So what are we doing here? So in that case, what are we going to do? We are going to mark the verb, okay, mark the subject of it, and mark the object of it, and that's it. We don't care about the word ordering. So for for languages like Turkish, this dependency graph is a better way of, more useful way of doing the parsing. Okay, so let's talk more about this dependency parsing. Okay, with the context-free grammars, this was the idea. We start with the words, and we group them into constituencies. And when you combine them all together, you came up with the whole sentences, or like bigger phrases like the cuddly cat by the door. Okay, that's what we did. Okay, so this is the context-free grammar stuff, and we said that Okay, these are not very preferable for languages like Turkish and Japanese or the Hungarian, etc. Okay, so and it causes these kind of problems too, and we don't care what the meaning of it. Some other, especially for the small or short sentences that are trying to express something, especially for the English language, these kind of stuff are common. They sound funny, but they keep using it. Do you understand what it is? San Jose cop kills man with knife.
The cop was with knife or the man was with knife?
You know which one they mean, right? Yeah.
Most likely.
The cops kill with their guns, not with knife. Scientists count whales from space. So whales from space.
Spatial weight.
So they don't mean this, right? They mean this. So both of them are possible. Okay, so these kind of things are possible. They are not going to go away. But maybe those are not important in terms of what is what. Maybe I should just do the dependency parsing and don't care about the ambiguity, because ambiguity will be that later. Okay, so this one is good. It's about Trump. No heart, cognitive issues. Trump doesn't have any heart, but he has some cognitive issues. I read it that way, but the doctor says no heart or cognitive issues. Okay. Anyway, these are supposed to be funny. You understand this one, right? So let's get the dependency grammar back to you. Okay. So arrows are our dependencies. Okay. Each node in this dependency tree is a word of our sentence. Can you read this? Just read this original sentence.
Bills on immigration were submitted by Senator
By Republican Senator. Right? Republican Senator Brownback of Kansas, right? Bills on parts and immigration were submitted by Republican Senator Brownback of Kansas. Okay, so these are the dependencies. Let's see the dependency labels. Okay, this is the root of the whole sentence. And nominal subject, bills. Okay, and this is the object, auxiliary, and this subject has modifier, nominal modifier, case, conjunctives, and the other stuff. Okay, so this is good enough for most of, definitely good enough for translation, right? Definitely good enough for translation. I don't have to group words together saying that, okay, I don't need to know the order of this grouping, okay? The senator, Republican Senator Brownback of Kansas, okay? I don't have to know the word order of it. Especially for Turkish, it doesn't matter anyway, okay? But I need to know the relationship between them. Okay, I need to know the relationship between them. I don't have to know the order of these, the object of the sentence, subject of the sentence, and the auxiliary verb. Okay, so this is called dependency grammar, and this is where we are looking at. And since this is not that strict about the word ordering and the constituency, I will not give you any nice and simple parsing mechanisms for this kind of dependency grammars, because most of the time when you make your decision You need to make this decision depending on the context itself. And if the decision is on the context, then you need to have some kind of a machine learning method or artificial intelligence method to make that decision. That's why where we are going to look at this machine learning and artificial intelligence based decisions. Okay, good. So, okay, arrow. This is the head. Okay, and this is the dependent. This is the head. This is the dependent for each binary relationship. Okay. By the way, this dependency grammars are older than the constituency grammars. People have been using them 5th century BCA for the Arabic language, right? That's what they say. Okay. First millennium Arabic grammarians. Okay. The Arabic literature people, they are very interested in writing poems and poetry and that kind of stuff. Very important. So their grammar is so. They had formal work about their grammars way before people started working on them. At least this is what we know. Okay. So with the context free grammars, okay, CFGs. So 1940s, then Chomsky, 1950s. We talked about them. Later they came back to this context dependency grammars, starting from 1960s, and now we are using it for languages like Russian, Chinese, Turkish, Japanese, Korean language, and etc. Okay. So, but let's take some break before I continue. When we come back, we'll talk about these relationships between the words, and we are going to look at least one way of parsing sentences using dependency grammars. Okay, 15 minutes. Let's be here around 35.
Bir şey yapar mı kaç?
Aslan ötesi. Sarayla Fatih yeter. Sarayla Fatih yeter diyor. Seni unutmaya ömrüm yeter.
İlk yarı yarısını. Ben biraz başladım da.
Tablom oldu mu? Kardeşim o tabloyu oluşturacaksan önce kaç tane farklı şey olduğunu bulacaksın. Gece olduğunu bulacaksın.
Onları yaptım da.
Ondan sonra. Ben yine oluşturma yani.
Onları yani işte. Tabloyu oluşturmak da yani. Bir kelime var. Biz yerden sonra çalışmak. Ona çalışmak lazım. Kaçalım ya. Kaçalım. Yazmalar. Sabit kal. Hepimiz ortada. Hepimiz ortada. Ne olacak şimdi? Bir kez daha şansını denemeyecek misin? Ha, şimdi ders mi başlıyor?
Şener bana araba dediler. Bizim araba başladı, ona gitti.
Ben de oyalanmasaydım şu an atmıştım imzayı. Başka tanıdığın yok mu orada?
Sana ne var? Başka falan yok. Yani konuştuğun kimse.
Yani çok şeyse git o derse git.
Ya.
Şu eve ışınlanırsın böyle.
Can.
Gidiyor mu?
Sen biliyor musun?
Evet.
Ben bilirdim.
Nasıl?
Ben bilirdim.
Ay. Gidenler var ya. Haberin olsun.
Hadi.
Bay bay. Seneye görüşürüz cidden.
Yok, haftaya.
Nasıl ya?
Haftaya geliyorsun
Ha,
sen.
evet hafta geleceğim doğru.
Haftaya pazartesi sana seneye oluyor.
Hayır ya.
Değil mi?
Oğlum daha aradığım başındayız.
Aa doğru ya.
Bay bay.
Optimality mi?
So where is the rest of the class? They are gone. Okay. So usually we assign a root head to the sentence, and the verb is the first dependent of the root. Then everything depends on the verb. It modifies the verb of the sentence. Okay. Here is one example. Here are a few examples actually, taken from a data set. Okay. Why is the city called Miramar? Okay. And this is the root, called, adverb modifier, nominal subject, okay, determiner, auxiliary dependent, and etc. As you see, the dependency relationships, the number of them depends on the data set, depends on the what kind of tag set you are using, but the idea is the same. Okay, again the root is here. Okay, do you think there are any queries in Miramar? As you see, all the relationships. Again, when I convert this to a tree, okay, this is obviously a tree, I lose all the ordering information. All I keep is the dependency information. Okay, dependency information. Wait to skip this one. Okay. So what kind of dependencies we have? Okay, let's look at these. For example, these dependencies are usually between the nearby words, usually, mostly nearby words, and intervening material. Dependencies really span intervening verbs or punctuation. And let's look at some of the interesting stuff with this non-projectiveness about the dependency stuff. Usually, okay, our dependency trees, before we go to dependency trees, if we draw the dependency arrows like this, usually you don't see these kind of intersections. Okay, you don't see these kind of intersections. In fact, the only algorithm that I'm going to show you today cannot produce these kind of crossing, intersecting arrows between the dependency arrows, dependency relationships. These kind of dependency parsing grammars are, or the dependency parsing systems are called projective. Okay, if there are no intersecting arrows, then it is called projective. And the thing is that the dependency grammars are powerful enough to represent these kind of grammars too. So we are going to look at them. So this is one concern that we are going to look at. The other one is, of course, this is a tree. Tree means what? There is no cycle. Okay, there is a root. With the root you have these dependencies and other dependencies, and there is no cycle. Okay, there is no cycle, and that's why we call them trees. Okay, and we talked about the projectivity. There is an easy way of finding a dependency grammar out of a context-free grammar. Okay, if you have your context-free grammar, by defining the head and the root of each rule, you can come up with a dependency grammar. If you do it that way, then your grammar turns out to be a projective grammar. Okay, there wouldn't be any crosses like this. Okay, there wouldn't be any crosses like this. But projective grammars are more powerful, and they will be used. They are used for explaining some of the sentences. Otherwise, that wouldn't be explainable. We are not going to, but unfortunately, we are not. I am going to talk about projectivity in a few minutes, but I will not give you any solid solution for this problem, because the first, the grammar, the parser for the dependency grammars is not going to be that sophisticated. Okay. Theory normally does allow non-projective structures to account for the displaced constituents, etc. Okay, so again, the methods for dependency parsing, dynamic programming is available. Okay, but this dynamic programming method only works for the cases with heads at the end rather than in the middle, either at the beginning or at the end. So it's kind of a rare case. There are graph algorithms. You know the difference between a graph and a tree, right? In a tree, there is always a root for all the nodes, and there are children. In a graph, you don't have parent-children relationship. There are neighbors in a graph. And some people realize that if we start from the graph side for a tree, okay, if we start from a graph side for a tree, then we can model it as a graph. Later we can convert it to a tree using maximal spanning trees. You know those kind of algorithms, right? We can do that. And other one is constraint satisfaction. It is, you say that everybody is related to everybody. Just start eliminating some stuff. Remember our rule-based part of speech taggers? It works that way. This is the third kind of dependency parsing systems. And we are going to look at this one more carefully, actually, the last one. It's a greedy choice, deterministic dependency parsing, transition-based parsing. It looks like a normal programming language parsing system, but we need to look at some we need to use some machine learning stuff inside this system. Okay, so greedy transition-based parsing, that's what we are going to look at. Okay, it will not be possible to parse projective grammars with this one, projective sentences with this one, but it will be simple enough for us to understand what's going on. Okay, so as always, we will define our data structure. We have a stack, sigma, buffer, beta, and dependency arcs, A. At the beginning, these dependency arcs are empty. Okay, so our sigma is a stack. It will have at the beginning it has root and some elements in it. Beta is our buffer. It contains our words, book, that, flight. Okay, and dependencies are like this. There is a relationship between root and thing, and the relationship name is verb. Okay, so these are the 4 things that we are going to look at. It's called shift or reduce parser. Shift reduce parser. But when we are doing the reducing, we need to ask it to somebody else. That will be our machine learning algorithm. Okay, so remember at the beginning I start with the root, only root. These are my words and these are my arrows. At the beginning, arrows are empty, my words are in my buffer, and root is there. Okay, there is this shift action, left arc action, right arc action. Okay, let's look at this shift action. You know, prologue, right? It's very similar to prologue. Okay. This one, what can somebody read this to me? Remember, sigma is our stack, beta is our buffer, A is the set of arcs. What does that mean in terms of prologue notation?
Add the wi to sigma and remove it from beta.
Yeah, wi is the word at the beginning of the buffer, right?
Yep.
Okay, so push the word wi to the sigma, to the stack, and the rest of them will stay same. How about this one? So this is the shift, okay? This is for shifting operation. These two are the reducing operation. So what does this say? Say that if you have two words on top of your stack, wi and wj, okay, pop the word wi and put a relationship between wi and wj in our arc set. This is called left arc. Okay, and left arc means that from this center word to the left side. Okay, right arc means that if I have the same situation, this time do the other way. So how am I going to make this decision? Am I going to shift? Am I going to do the left arc or right arc? Okay, so we need somebody smart to make that decision, and usually they use machine learning systems to make these kind of decisions.
Couldn't we just make it statistical?
Statistical would be fine too. Well, machine learning means it is statistical, right? I mean, machine learning, yeah. I mean, training means that you gain your data from the data set, and if you do it your statistical way, I think you mean maximum likelihood estimation.
Yes. So which
Yeah.
one is more likely?
Which one is more likely?
J, wi, or something like that.
Yeah, given those two words,
Yeah.
etc. But gaining those kind of statistical data may not be that easy, because you might have say, okay, I have this word and this word on top of my stack, right? And you are going to make always the same decision if you are going to use the maximum likelihood estimation. So maybe you should consider what kind of other things you have in your stack, what kind of things are coming after in your buffer, and etc. Okay, so this is again basic transition based dependency parser. Since I am doing only left arc and right arc from the top of the stack, it is not possible to have arrows crossing each other with this situation. Okay. So basic transition based dependency parser. One example here. Okay. So at the beginning, I have this I ate fish. Okay. So this is my stack. I have root in it. I have my buffer. I ate fish. Okay. Three things I can do: shift, reduce arc left, reduce arc right. Three things. Okay. So at the beginning, I am going to make this decision. I am going to ask my oracle. Sometimes they call it oracle. I am going to ask my oracle, what should I do? It says shift. Okay. I shift it. I put this I at the top of my stack, and I shift again. I 8, and then if I continue, okay, I did the left arc. What does left arc mean with this nominal subject? Okay, I depends on this 8, okay, and the relationship is the subject. I is the subject of 8, and then I shift again. Okay, so by shift I mean I put fish into my stack too, and my buffer is now empty. All I can do is left shift or right shift. Okay, right, left arc or right arc, In this case, I am going to do a right arc between those two. 8 and fish, there is an object relationship. 8 stays in there, and then between root and 8, it is the verb, okay? Root relationship. So what do I have? I have this, okay? Root and 8, there is a root relationship. I is the nominal subject of 8. Fish is the object of 8. Okay, so again, 3 things. Should I shift left arc or right arc? Who is going to make this decision? Again, it's either something rule-based. If this and this happens, then do this. Otherwise, I am going to use a machine learning method. But for the machine learning method, I need a data set that marks all the relationships between the words of given sentences for maybe hundreds, maybe thousands of sentences. Okay, so this algorithm doesn't answer any of that. How to choose the next action? Okay, and there is no simple search. It is just linear. You just read it, left arc, right arc, or shift. That's it. Okay, it provides very fast linear time parsing with very good performance. Okay, let's look at this. Let's look at this machine learning stuff. So how am I gonna make that decision? Okay, given a time, given a step of the algorithm, this is what I have. I have my stack. In my stack, I have those words, the top word and the previous word, and I have my buffer. Okay, so this is the current situation. I can keep all that data. I can keep all that data in a vector form. Okay, so what kind of features I can keep? I can keep the part of speech tags of these words. For example, this good is adjective, this is verb, this is nominal noun, and etc. Okay, I can get all of those features and ask a machine learning system to make a decision for me. Okay, very large space. Okay, sparse and very large space, and just make a decision out of those for me. Okay, and it makes a decision, and this decision is based on the training set that you had introduced before. Okay, that's it. I mean, I'm not going to give you any. I'm not going to give you any machine learning based. Any dynamic programming based parser for this one, or any kind of algorithms that we have looked at so far. It's a very simple parser. Its performance is based on the performance of this machine learning method that makes this decision. What are those words? What are their types? And what are the words in my buffer? What are their types in terms of part of speech tagging? Okay, these are some of the, some people say that let's do this kind of stuff. For example, if S2 stack 2, S2 has, and S2 type is WBZ, okay, the verb tense, and S1 W is good, then this is one feature, this is another feature. So these are all handcrafted features. Some other people say that don't do any handcrafted features. Let the features define themselves by using the raw words and etc. I will not talk about them. But the thing is that how are we gonna measure our performance with the dependency grammars? This is what you do. Okay. If this is my sentence, she saw the video lecture. Okay. And I mark it this way. There is a okay, the relationship for the she, let me do this way, okay. What? Okay, so between 1 and 2, between 1 and 2, 2 is our verb, okay, there is a subject relationship. Between 0 and 2, there is a root relationship. Between 3 and 5, there is a determinant relationship, etc. This is the golden standard. This is the ground truth comes from the data set. But this is how I do the parsing. After the parsing, I came up with these results. Okay, so I think I recovered this one, 1 and 2 she, 2 and 0 so. There is a problem, I think, with this rule, right? The rest of them is fine. Okay, 3 and 4, the video, yeah. The correct one is the lecture, right? It's not. The is the determiner of the lecture. It is not the determiner of the video. So how are we going to measure the performance of this parsing? Number of correct dependents and number of dependents. So there are total of 1, 2, 3, 4, 5 dependents. 4 of them are correct. So I am doing, okay, I am doing 80% correct. Okay. So this is the accuracy of my dependency. This is one way of measuring our dependency for the our accuracy for the dependency parsing. How about the projectivity? As I said, this one, the algorithm that I showed you here, cannot achieve projectivity. Okay, cannot achieve projectivity. It all has to produce this kind of stuff, because given a word, okay, given a word, it either connects to the right or to the left. And once it sees the word, okay, once it is reduced, it doesn't come back. Okay, so it cannot handle the projective cases. But sometimes we have to behave like a projective case, like this one. Who, well, I mean, very rare sentence, but it is valid. Who did Bill buy the coffee from yesterday? Okay. So, who and from. Buy is definitely the root, right? This is the root. And if I draw the root, it's definitely going to either cross this one or definitely cross this one. So who is making a problem? So how am I gonna parse those kind of stuff? Okay. First one, the one that we like most, we don't handle it. Okay, we don't parse those kind of sentences. The second one is dependency formalism, which has only projective representations, context-free grammars. Okay, with the context-free grammars, use such context-free grammars that doesn't allow any projectivities. So your grammar is going to be a lot more complex than it needs to be, because you are not going to allow any projectivity. Or parse it using non-projective mechanisms like that. Post-processor comes back and checks if there is a projectivity is happening. Okay, that's the other thing. And let's skip this one. And for this one, it says that, okay, don't treat your grammar like a tree. Treat it like a graph. Okay, so these kind of parsers are the most general, more difficult to implement, and algorithms are difficult too. It's called maximal spanning tree parsers. Okay, so it is trying to find the tree out of a graph. So projectivity doesn't mean anything for that one. It already satisfies that kind of picture. Okay, maximal spanning tree stuff, graph-based dependency parser. Okay, so I guess that's what I am That's marks all the things that I like to say about the dependency grammars. I couldn't give you, as I said, a very nice examples of the parsing sentences, because as I said before, your shifting, your reducing depends on your decision, and your decisions come from the machine learning stuff or the other kind of stuff, context stuff. And for that, I need to have some kind of a machine learning system, and it is not easy to show those kind of stuff on slides. Okay, the up to now we have never needed any data set to produce a parsing tree for any kind of sentences, because for the context free grammars, you have your grammar, you have your sentence, you parse it. This one, it needs it, because it needs the context information. The author of our book, no, the author of these slides, this guy Manning, he said that they have developed a neural network based dependency parser, again another machine learning system, and it says that they are doing very, very good compared to other types of dependency parsers. Really great results. Okay, good. Any questions so far? So I will stop talking about dependency parsers anymore. We will start talking about more modern ways of doing natural language processing and generation. That means we will start talking about neural networks. And let me go to the slides of Manning again, neural networks. And let me open it. Some of the stuff I talked briefly a little bit about at the beginning of the semester. Some of them are new, and some of them you already know it from your machine learning courses, or maybe some of you took deep learning courses. But these are nice because we are going to talk about the machine learning or the neural networks in terms of natural language processing. Okay, so if you are doing machine learning, you have to have a data set, training data set. Somebody did stuff like they sat down and they marked each of the words, like this part of speech tagging. Okay, this is verb, this is adjective, this is noun, and etc. Or they said that I would shift at this position, I would reduce at this position for the dependency grammars. Or they said that, okay, as a constituency, I would mark this part as a verb phrase or the noun phrase, etc. So that's called the training set. So this is how we represent the training set. We say that Xi's are our inputs. I don't know what Xi's are. Maybe they are our words, maybe characters, maybe sentences. Xi's are inputs. Yi's are our labels. Okay, they are labels. So our labels could be part of speech tags, or if Xi is a sentence, Yi may be true or false. True means it's a positive sentence, false means a negative sentence in terms of sentiment. So classes could be sentiments, named entities, by self decision, etc. Okay. So this is how we represent our training data set. It has to be prepared by somebody, some people, and of course it involves people's subjectivity. With NLP, that's one of the problems that we need to deal with, but we can't do anything about it, so we will accept it. Okay? Usually we visualize our data this way. Our Xi are inputs, right? Usually our inputs are very high dimensional inputs. What do I mean by high dimensional? Remember our word to vec? What was the average the word dimension to represent a word in word to vec? It was like 200 dimensional word, right? If I have a sentence of 10 words, 200 times 10 is 2000 dimensional vectors as an input. Okay, it is very difficult to visualize those kind of spaces. So usually we just visualize what we can visualize best. We visualize two-dimensional spaces. We say that, let's say I have a two-dimensional input vector xi instead of 2000 dimensional. Okay, and I am going to draw a line in this space like this one. Whatever remains on that side will be positive. Whatever remains on this side will be negative. Okay, so visually we try to show our algorithms on two-dimensional graphs like that. Well, you might say that isn't that too simple, too simplistic approach? Well, it is not that actually, because any mathematical procedure that you can do with the two-dimensional vectors, you can do the same thing with 1000-dimensional vectors too. That's why we like these two-dimensional stuff. Okay, so we fix two-dimensional 2D word vectors to classify. Okay, and usually this is the first machine learning stuff that we can achieve. Okay, let's look at this one. This is called Softmax, Logistic Regression, whatever you call it. Okay, Softmax or Logistic Regression. We say that given your input x is a d-dimensional vector. Well, in this case it is two-dimensional, but it is d-dimensional. Remember, in our case, if a sentence is 10 words and if each word is 200 dimensional, that means that for that sentence I have 2000 dimensional input. Okay, this is a vector, and this is a set of weights w. Okay, w is a set of weights. It is C times D dimensional matrix. D is the number of dimensions of the input word. C is the number of classes. Okay, let's say I am doing part of speech tagging. Okay, part of speech tagging. Then let's say I have 10 classes: verbs, nouns, adjectives, adverbs, and etc. Okay, so C is going to be 10. Okay, given a 10 word sentence, I like to say the part of speech tag of the center word using this notation. So I am going to multiply, let me do this. Okay, this is my x, this is 2000 dimensional. Okay, and this is my w, weight. Okay, so this one is 2000 by, there are 2000 elements in it, 2000 columns in it, 2000 columns, w, and the number of classes is 10. Okay, so if I multiply this 2000 by 10 matrix with 2000 factor, what would I get?
10 vector, 10 by 1.
It's going to be 10 by 1, right? It's going to be a vector of 10. Okay, a vector of 10. That's what I am doing here. Say that, okay? Multiply the row number y with vectors. That's what I'm doing actually. Multiply the row number y with this vector and get just one number, or do this one by one for the whole matrix. So let's remember this multiplication thing. If I have a vector like this, let's say it is 2000 dimensional vector, another 2000 dimensional vector. If I multiply these two, what would I get? I would get a simple scalar, right?
Yeah.
Just a number alpha. So what is the meaning of this dot product? Usually we do this kind of dot products, okay, to measure the angle between these two vectors. Okay, if these two vectors are very similar to each other, I would expect the angles between these two vectors to be similar. Okay, to be very small. The angle is very small. If they are the same, okay, the angle should turn out to be 0. Okay, so dot product actually is trying to measure how similar these two vectors are. Okay, if they are very similar, I should get a large number for that one, because remember the dot product is measuring the cosine of the angle between these two. It's going to be large, it's going to be close to 1 for the exact cosine measurement. If it is perpendicular these two, you are going to get a 0. That's kind of what we are doing. If I get one of the rows of this matrix, large matrix, multiply it with this input, okay, if that row is similar to my input, then this number is going to be large. Okay, and I am going to do this operation for all the elements of the matrix W, for all the rows of it. Okay, for all the rows of it, one by one. Each row represents a class actually. So what does this mean? I am going to multiply myself with all the rows of this weight matrix. Okay, and by doing this, for this class Y, I am kind of comparing my similarity to that class Y with the rest of the class elements. Whichever I am more close, this probability will produce a higher value. And that's how I define this probability. Well, probability means that this has to be between 0 and 1, right? Is that, do I satisfy this constraint? Is this going to produce a value between 0 and 1? Do you think? What is x? Of course, x means e to the power something, right? Is this going to satisfy that constraint? My value is going to be between 0 and 1. By the way, what is the range for the alpha? Can it be a 0? Yes. Right? If the angle between them is 90 degrees, it's going to be 0. Can it be 1? Yeah. If they are completely the same, yeah. Can it be a negative number? Yes, because the cosine, yeah, it could be a negative. So if I multiply two vectors like that, it can produce a negative number. With the probabilities, what am I going to do with the negative numbers? That's why I have this exponent, right? E to the power something. E to the power something will never, let's remember e to the power something. E to the power something is this, right? Okay, so what is this number? E to the power 0 is 1. E to the power 0. E to the power something to the power 0 is always 1 other than the 0 to the 0. Then, and e to the power 1 is e, right? Yes, e. So if I put this number to the e to the power, this will definitely be a positive number, and this one is going to be definitely a positive number. So we handled this positive thing. We use this exponential for this positive numbers only. Okay, that's good. So let's look at this one. Is this going to be between 0 and 1 for the probability? The answer is of course yes. Why? Because this is just one of them. Okay, when C becomes Y, I am repeating this here, right? So this upper part will be definitely smaller than or equal to this one, and the upper part will definitely be greater than 0. Okay, so this P given X, Y is definitely be between 0 and 1. That's good. How about this then? How about this then? What are the probabilities of given X? Okay, what are the probabilities of all the Y's, the total of them, all the Y's, I mean all the part of speech tags. So the probability, the summation of the probabilities are going to 1.0. So this is something good. So this probability definition, I just defined it, I just made it up, turns out to be good, okay? It is between 1 and 0. It is using this cosine thing, the angle thing. So all I'm doing is that given the input feature vectors, I am trying to compare it with my weight matrix, like this W, okay? And I'm doing this division, and I'm getting a probability back. The thing is that if I can choose these weight matrices, the numbers in a sensible way, then this is very nice. This is a very nice machine learning algorithm, because I am training my W's depending on my data. Whenever a new data comes in, all I'm doing is to multiply these two numbers and do the division, and come back with the result, the probability of having that class. Okay, so that's the basic definition of the softmax regression, or the logistic softmax function, or the logistic regression. Once you have that W, you can do this simple math, and you will do these kind of classifications in a linear space. Okay, so next week I am going to continue on this. Sometimes we say that this is too limiting for us, because all I can do is to draw these kind of lines in 2-dimensional or 2000-dimensional world. I need these kind of classification techniques too. So what am I gonna do with those? We will talk about them, and we will see our first application of natural language processing on the neural networks, named entity recognition. We are going to try to look at this one. Named entity recognition, as we looked at before. Okay, find and classify names in text, for example. The European Commission said on Thursday it disagreed with German advice. So European Commission is organization, German is miscellaneous, France is location, Britain is location, Fischler is person, etc. So we are trying to assign tags to each of the words. Sometimes we say it is other. Okay, so it's like part of speech tagging, but we are giving semantic names, semantic classes for some of the words. This is very useful for information extraction. This is very useful for question answering, because you don't have to parse the whole sentence to do the information extraction. All you need is just what is the organization, what is the person, etc. Okay, so we are going to apply the softmax classifier for this kind of natural language processing problem. Okay, thank you. That's it for today. I will see you next week. So what is this group and what is that group?
Clusters. Machine learning.
It's just clustering, two classes.
People in the middle went
Hocam kaç tane daha ödev olacak?
Efendim?
Kaç tane ödev olacak?
2 tane daha ödev olacak. 2 de makine öğrenmesi olacak. Toplam 4 ödev. 3'ünü kesin yapmanızı bekliyorum. Lisansüstü öğrenciler tabii ki proje de yapacaklar. Pardon, paper presentation yapacaklar. Lisans öğrencileri isterse yapabilirler bonus olarak.
Efendim?
Bonus olarak lisans öğrencileri de yapabilirler şeyi.